Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're gonna talk about something a bit more imaginary. So this is my plan for upgrading ISRO. Basically, this is just a thought experiment. So if you get kind of you don't know anything or something like that, please dislike the video and leave the video because this will be a long video. So let's dive right into it because it's just a thought experiment. It's like, what will I do? Well, first thing, I will cut ISRO in two. Now, part A, meaning the first thing, will be everything without the basically launch provision, meaning there whatever ISRO does after the rocket has been launched, meaning once the satellites are in orbit, who takes care of it? That's ISRO part A. That's the whole point. And the other part will be launch service provider, or it can even be renamed as Indian launch service provider, whatever have you. And you may be like, is there a precedence of doing something similar to this? Well, similar, yes. ISRO, I'm saying basically NASA did something similar in launch service program. This was done after basically space shuttle was retired, and it was done in 1998. Now idea with this is like they realized very early on is like, because if both of the things are combined, meaning launching and managing assets in space are done by the same people, you have a very serious lack of accountability, meaning you cannot call up, it's like, okay, who messed up, like what's wrong, like if you want to, I'm not talking about like in terms of blame game, but you need to sort it out. It's like, what happened, what went wrong? You won't get any answer because it's like, yeah, that's all they were getting. That's why this 1988 project was, and that's why SpaceX has a basically NASA has a whole pipeline of how they're gonna give contracts to ULA, how they're gonna deal with SpaceX, how they're gonna deal with orbital ATK. You get that point? Like they developed all the paperwork, all the pipeline, and this literally allows with accountability, meaning if let's say tomorrow a Congress or government or whatever have you comes out, it's like, dude, this project should have been done at this budget and it's not working, you can figure out it's like who is to blame and like who messed up the most or what went wrong. Like for analysis, development and refinement, these things are like compulsory. You have to have accountability, and then it also improves transparency. It's like, who messed up? It's like you need to know who messed up. Like, did the integration partner who was supposed to integrate everything, they messed up, or is like what actually went wrong? So you need that transparency. It really helps. And this, in case of India, it will really help private investment, because right now there are some companies that are trying to, because again India just recently passed a law that allows private companies to actually launch stuff. So India is really behind schedule. However, on top of that, because ISRO is not in two parts and there is no framework similar to launch service provider, like it creates a conflict of interest, because India is such a behind schedule right now. Even if let's say they make a very good small satellite launch vehicle, who's gonna order it? Because right now you have Rocket Labs that have been successful, you have ride sharing from SpaceX, which is hyper cheap, and then you have Astra that have already launched. You also have basically Dragon, the Dragonfly that's supposed to be launched very soon. So you get that point. Like that behind start is very serious. And once you cut ISRO in two parts, that creates a definitive incentive for small companies to now they have an actual chance of winning, because right now ISRO literally created their what we call own conflict of interest. All these small companies are making small satellite launch vehicle. What does ISRO do? Small satellite launch vehicle, SSLV. Why? Like, do you want any of these private companies to succeed? It's like, why are you competing against them? It's like, have some faith in them. And like this was ironically retirement of SpaceX was like the SpaceX, I'm saying, space shuttle was the best thing for NASA, because that created this framework where people were like, okay, we have to trust some people, we have to take some chances, we have to take some gamble, and that gamble yielded to SpaceX, and right now they are ruling the world. And that's the whole point. You have to give them some opportunity to grow. That opportunity can only come if ISRO has hey, I do not care who is launching my rocket, as long as you are launching my rockets, or my payloads. So you get that point. That boost in private investment, because there are more than enough millionaires and billionaires in India. Yes, I'm talking billionaires, more than enough out there. But like again, nobody's investing in rocket industry, because like ISRO itself is competing. It's like, what the hell? Private company outside markets is already pre-saturated, and like in terms of small satellite launch vehicle is like, who is gonna launch it? That like if ISRO has like, hey, I have this rocket, versus a small startup, it's like, I have a rocket, who's gonna trust this small rocket? That's the whole thing. So this reduces conflict of interest. It's really important and necessary. Basically, it also helps with accountability, transparency, reducing. It's a really good thing. Just cut ISRO in two parts. Now, what will the second part, basically the rocket launch provider, will gonna do? Well, they're gonna build one rocket, and this is one thing India has to learn, and I am genuinely surprised like they're still not learning it. Is like, every rocket that India has is literally built in 1970, and I'm not talking like built as in like physically built or designed, physically designed. It's like the principle of design that went in all those rockets are written in 1970. That's why India has such a poor rocket systems. It's like hyper expensive, ludicrously large amount of part counts, and really bad track record. and like very low cadence. That's the thing. Like, to give you a context of that, ISRO is almost 50 years old, and it has same launch cadence as something like basically Electron Labs. How the heck that was possible? How the heck something that is like 16 years old came close to launching? You may be like, okay, their rockets are smaller, but here's the, they are launching it, and their speed, their trajectory is much faster. Like, at their current rate, by the time they are like 2025, they will have like, neutron rocket, and that point is like, yeah, they already surpassed it. Like, think of it this way, like, they somehow surpassed a 50-year-old company without any issue. It's like, how the heck that happened? That's the whole thing. That fundamental principle is corrupted. Like, last time some people asked me, it's like, I did find a lot of flaws. It's like, what will I do differently? This is the second thing. One rocket, that's it. Like, one goddamn rocket, and the whole point of that rocket would be mass producible. Right now, India's biggest rocket is GSLV Mark 3. It's really bad rocket, not in terms of like bad as in like bad, as in like it's built in 1970. The design is in 1970, meaning it has way too many parts. It has solid core, it has support cores. It's like way too many things it has. So meaning, even if government is like, okay, go YOLO on money, please launch our Gaganyaan mission, basically Indian astronauts, they can't do it. It's like, simply because the rocket is inherently has too many parts, inherently has too many supply chains, inherently not mass producible. That's the first goal. This one rocket will, like, basically we are going Lord of the Rings on it. It's like one rocket, mass producible, meaning I got this. Like, that's the step one. Second, what is the tonnage capacity? Focus on 30 ton. Now, this is what we call some heavy lift capacity. And why 30 ton? Well, 30 ton because, again, I do not want India to be like, oh, we are so poor. No, we are not poor. We have like 1.5 goddamn people. And it's like, we have surprisingly large amount of money in India. I mean, like, India is not a third world country. Like there are third world countries. And once I have seen that, like, once I've studied them, it's like, okay, India has more than enough things. We got this. Like, again, we are not the best of the best. We are also not worst of the worst. So we're not going to make a toy rocket. 30 ton. Now, 30 ton is a good enough capacity where even if you're launching something to geostationary, you're going to have some serious capacity there. And even if you're reusing it, even if you lose that 30 ton capacity to very low energy, you still have more than enough. And if you have to like launch something big, something massive, let's say a giant space station, 30 ton, I got this. And this creates another green opening, that it will give startup a chance to actually fight and actually give them the drive. Like SpaceX, a lot of people are very driven there. Now, many people are driven for the Mars project, but here's the deal. Before that Mars hype right now that there was a hype to get America back to space, because America is the only country in the planet that had their own astronaut program and they had to cancel it, meaning they have to take a phone call, very expensive phone call to Russia, and it's like, can you please launch our astronauts? That's really not desirable. Like, think of it this way, like their kids literally went from, yeah, USA can do it, to like, yeah, we have to go to Russia to launch our astronauts. It's like, that happened. So that gives them another drive. Now, same thing will happen here. It's like, if ISRO flat out says like, hey, we have nothing right now, make sure your rocket does the job, every Tom, Dick and Harry will be driven, and that creates a very good drive, financial incentive that you really want to milk. So it will take care of the private sector. Now, the basic design of this rocket will be done in 1 month. Now you're like, wait a minute, no rocket can be designed in 1 month. Yes, absolutely true. But base design can be easily done in few days, basically. Now, meaning you get the people together, you sit down, you calculate the numbers, you're like, okay, can it mathematics allows it? Can physics allow it? Can engineering allow it? Basically, rough diagram. And that's why, like, you will notice SpaceX does not have full design of Starship, but they are building it. How? They did that rough design, like a rough draft, meaning this sort of thing, and they are starting to refine it as they go. So same project here, 1 month just to figure out. It's like, okay, my aim is 30 ton and my diameter is 6 meter. Now that diameter is fixed. Now primary reason for that is 6 meter is huge. To give you a context, that's like bit 0.5 meter wider than the Vulcan rocket, and like that I think 0.5 from Ariane rocket also, but not too big, because again SpaceX did learn the hard way. They wanted like 12 meter. That would be awesome, but they figured out like handling a 12 meter article is too goddamn complicated. 6 meter is doable. India right now has a holding capacity of 4.5 meters. 6 meter is not too bonkers. It's like, it's bit of effort, but can be done. 6 meter. And again, fairing capacity will no longer be an issue, which is a very big issue with SpaceX. It's like, our fairing is too goddamn small. America is like, I'm not joking, SpaceX actually sued US Army second time, and this time it was not Army, it was the National Space Agency, basically Space Corporation, Space Force, I think. And they're like, yeah, you'll watch. It's like, they are the service provider. It's like, dude, my satellite, I decide what kind of fairing I need. You don't tell me. It's like, so that's why big fairings, no compromises, no BS. 6 meter diameter. Now, having this diameter has the big fairing, and it also reduces height. So basically, it will not become ludicrously tall, which was a very big issue with basically Falcon 9. Falcon 9 is basically very compromised rocket because of its thinness. Now you're like, why the heck they made it thin? Again, they have rocket scientists, then why did they make it? They were poor when they built it. Now like, what does that have to do with anything? Well, because they wanted to use normal road structure, meaning they did the maths and they figured out if they keep it below 5 meter, they have a very good chance of transporting it anywhere using normal roads, meaning almost all bridge clearances, all flyover clearances will be cleared, meaning they will not bump into anything. They can use normal road and they will only need to, like, block that road for a very small time, because if you block it for a very long time, like when people are transporting very heavy equipment, it does cost boatload of money. So they did not want to spend boatload of money, so that's why. And that's the first thing, like, think of this, like what Electron Labs are doing in neutron rocket: make it fat. What every Tom, Dick and Harry is like, when they can do it, is the first thing they do it, make it fat. That's the whole point. 6 meter. Now base design, so base design only has these two criteria right now to bind it down. It's like 6 meter 30 ton as quickly as possible. Rough idea, just rough idea. And this from day one has to be designed in multi-stream parallel development protocol, meaning whenever you are dealing with some sort of development, be it software development, be it rocket development, there are many things that are interdependent, meaning A has to be done before you start the B. However, it does not go throughout the alphabet, meaning you will have A and B are interdependent, so you can only do A. Okay, awesome. How about C? No, you can start C from day one. How about D? Like, no, you can't do that. E, no, you can't do that. F, you can do that. Like this sort of things goes on. Like in every project, if you sit down, even if you think like, okay, it has to be done step by step, you will find that no, many things can be done parallelly. And this is the reason why companies like that are barely like 5 years old, like think of it this way, like Astra is 5 years old, already went to orbit. So that's the whole point. There are many things that can be done in parallel stream, and this has to be in that 1 month. Like when they are hashing it out, they have to find out like these things can be done, and I'm going to give some examples of that. So 6 meter development, and which material to use: stainless steel alloy. Now primary reason for that is like, again, it's cheap. SpaceX is also using that now, and benefit of that is like you can even do alloy mixing. For example, they started with 301, then they went to 303, now they have 30X, which is their custom mix. Again, because they are dealing with cryogenic, they have figured out like some advantages where there's like in their use case that steel would be awesome. You will don't expect that 30X steel to become normal thing. Maybe they're a patent issue, or maybe they're just like, yeah, it does not serve you unless you are carrying liquid methane. So in those sort of scenario, you will find out. Now, what's the price difference? Like right now, majority of the rockets are built from what we call lithium aluminum alloy mix. Idiotically expensive. To give you a context of that, that's like 4,000 to 5,000 rupees per kilo, and compared to stainless steel like 301, that's 50-60 rupees. Like that's like multiple zeros are difference is there. So that's why it has to be done with stainless steel alloy. Now again, ISRO may develop their own custom alloy for their needs, or maybe like, yeah, 301 is like good enough. It's like it is good enough, it does work, so it's good enough. Now what in terms of main propellant, CH4 and O2. Now CH4 is not necessary from day one. You can still use heavier hydrocarbon, and performance will not be too bad. Like you can get close enough, but again, you do not want to use very heavy carbon chains, because again, then you have issue of soot production, which only happens if like RP, you go to liquid fuel. Gaseous fuel is not supposed to have that much issue, but again, if you're using butane, ethane, propane and things of that nature, you may have some slight soot production, but generally lighter methane source series, you should be okay. Now O2, ISRO already knows how to deal with that. CH4, it's a bit new, and it will be the propellant. Now the primary target would be hot gas pressurization, meaning when you are talking about huge tanks, which yeah are 6 meter, it's huge. The only thing huger is the basically space shuttle main tanks. They realize that like you cannot pressurize with any other third-party equipment. Like there is no third party that you can carry, even helium. So what they did is like basically had the gas boil off, basically hydrogen, boiled it off around the engine, and then send it back into hydrogen tank. Took oxygen, boil it off, send it back into basically oxygen side, and that's how they pressurize huge tank. And you have to do it here. So that would be from day one. And nitrogen third tank. The third tank for nitrogen would be for auxiliary needs. For example, spooling up the turbine, flushing the engine, because if you want to restart your engine, you need to flush it out. Again, not necessary in some engine geometries, but in some like you have to flush it, otherwise it's gonna go boom. And again, spooling up, it does help you. If you have it, it does help. And cold gas pressure. Again, without it, you simply cannot reuse your rocket properly in space. And there will be two mode of usability. First, disposable, meaning you just launch it, forget about it, and then you have return to land. Now, like, why not catch on the sea? Reality is sea assets are too expensive, like ludicrously expensive, idiotically expensive. And India is very close to equator. Sea is not kind there, so it's a very, very expensive. Again, SpaceX is also having hard time, like, and that's why like when they are figuring out space assets, like basically sea assets for Starship, like they have to have huge oil rigs to deal with that. It's very expensive. So no, and for 30 ton, like that's not desirable. Like again, it's still, if it can still launch, let's say 10 ton when returning to land, more than enough. That's like, don't even worry about it. Now, I specified there are many streams that can be done parallelly. So the first stream that can be done very easily, that is stream. Now, this is the first thing that will be finalized, because all you need to know in the start to development of tank, you need to know the height and the diameter. That's it, done, go home, sweet dreams, start working on it. And what ISRO has to focus on in this time is like supply chain. Can this metal furnace can provide, or like for not furnace, I think like this company that is claiming that we can provide you like let's say 30 ton per month, can they do that? Again, you can test it out from day one, like okay, and this how many suppliers are there? You definitely want 2 suppliers at least. You get that point, and you can test the alloy mixing, because be mindful, surprisingly large amount of people cheat you in alloy mixing. That's why people have developed like portable laser spectrometer that you're gonna boom a surface in that and then study the spectra, and then it's gonna turn no, this alloy is not the right alloy. I'm genuinely surprised how many people are cheating you on metal. So you have to like ISRO has to be like double check, triple check everything. And the key goal at that point in time is like manufacturing improvability, meaning why the heck do you think Vulcan is so expensive? SLS is so expensive because if you take the tank rocket, just what do you see at the rocket at the most of the time is you look at the goddamn tank. Now if you open the tank, you will find there is ISO grid in it, meaning it was a sheet metal, like very thick sheet metal, as thick as like 1 inch or like 3 centimeters, like very thick metal. And then they CNC'd out giant of thing. Now you may be like, wait a minute, that will waste 90% of the material. Yeah, they did. That's why it's so expensive. Like not only you're taking material and you're poofing 90% out of it, you are also adding machine time to it. You're also adding the cost of the machine. You're also adding cost of the drill bits that's gonna wear out. All those things pile up the cost. So basically, what SpaceX realized is like, hey, can we just have stainless steel and just roll it, weld it, go home, sweet dreams? Yes, they can do. That's why they could do so quick iteration. Right now, they're waiting for FAA approval, not because they can't develop it. It's like, we got this, man. We got this. That's the whole point. We have to figure that out. Like none of this, like ISO grid, hulu, no. Simple, elegant stainless steel construction. That's the whole point. Key goal on manufacturability. Nothing else matters. Like, can we manufacture this as quickly as possible? Because even the baffles that are inside the basically the system, it's not that complex. It does not need to be complex. It does not need to be ISO grid and hulu. It's like simple thing. It can be done. And small testing, small scale testing, which can be done very quickly. It's like, okay, we got that, like first spool, stainless steel are generally sold in spools, like very big spools, and that spool, once you got it, you can start building it quickly. Like you can start testing with like same thing as SpaceX is doing. Everything you can follow that is like nitrogen testing, pressure testing, liquid methane testing. You can do everything very quickly on. It's like from 2 months you will be like, okay, now you are actually building things, you are actually testing out. Then if the height and diameter is finalized, you can also build full scale mock-up like this puppy and this puppy. Now the mock-ups are really priceless. Like before that, people are like, who builds mock-up? Right now they're like, no, build the goddamn mock-ups, because it saves time. Once you build the mock-up and you load it up with the correct weight, expected weight, and then point you can hire the trucks and you can test it out. Like, is that truck is capable of carrying it? How much road clearance do I need? How much time does it take from traveling from point A to point B? Either A, you can predict it, or B, you can actually shift it and figure it out. So every company, be it SLS, be it Vulcan, they have learned it the hard way. SpaceX also is like, no, man, just build a prototype, like a real world full scale prototype. Nothing beats it. You will figure out everything. For once you build a full scale, you can do the calibration. It's like how big the robotic arms should be, like how the clamping mechanism, all that jazz will be. And full scale rehearsal is like, how do we do all the steps? These are priceless things, and you can do it very quickly on. You do not need to wait for design to be finalized, because it will not change. Like, what's going to change? Height could change a little bit, diameter could change a little bit, but more or less it will still be the same thing. So it can be done. Now let's talk about engines. Now engine is the heart of the system. Now if this does not work, everything else is poof. So what we have to do? Well, it has to have some goals here. Now primary goal, it must have electrical restart capability, meaning like how space shuttle main engine had electrical ignition system. That spark wheel you see, that spark wheel is there to burn off spent hydrogen, not to actually ignite the engine. That spark chamber is actually inside the engine. Now that's something similar has to be done here. So it can be restarted in space and multiple times on the launch pad or anywhere you need to. So that's the whole point. And you really do not want to rely on TTAP, which is like, oops, SpaceX have lost actual rockets because of oops, they ran out of TTAP. You really don't want that. You want electrical restart capability, and it reduces component count. That's the whole thing. You want to reduce as many component count as possible. So it has to be sea and space. Basically all engines are sea and space. It's just like that ISRO's mentality of 1970s, where they did not knew that, hey, same engine can work in higher altitude. All you have to change is the engine bell, nothing else. It's like that. Like we did not knew enough in 1970. Again, rocket was very new at that time, but right now it's like, yeah, every company that figured it out is like, okay, same engine, control C, control V, just change the engine bell. They are printing money. Everybody else is like, yeah, our rockets are too expensive. So that has to be done. Now engine development does take time. Now, not the development, not the mathematics part of it, not the designing part of it. What does take time is like actually manufacturing basically injector plate and turbo pump assembly. These two things are idiotically complicated. Thankfully, at this point in time, as in like 2022, 3D printing, metal 3D printing has reached full maturity. Meaning, at this point in time, you can give your money, get a proper printer, print out a basically turbo pump assembly and basically injector plate, and be done with it. Like right now, it's not something that may happen in the future. Right now, people have engines, actual engines that are using this. So this is NASA, from NASA. So be mindful. This is one way they can speed up process, and this also has another advantage of that you can iterate once you are done. It's like, okay, this engine works, okay, how about we change the something little in injector plate and see does it improve performance or not. You can do that. How about in turbo pump? These two are the core of the engine, and you can go YOLO on it if you have 3D printing. And the main focus is on mass production. Can you produce it as quickly as possible? Everything else can be basically seconded. Like, if you can produce it as quickly as possible, it's good. If you can't produce it as quickly as possible, don't waste your time on it. Like every aspect of the design, it does not need to be the most powerful, the most badass engine. No, it has to be efficient and basically restart capable, and it has to be like, okay, I can iterate on it. So to give you a context of that, like the Falcon 9 Block 1 was barely able to do 10 to 15 tons, barely. Right now it does 23. Why? What changed? Nothing else other than the engine. So that's why you do not need to reach perfection in day one. You can just work your way up to it. So that's the engine part of it. So now let's look at another string that can be done. Now be mindful, I'm just looking at some few things. Other things can also be automated. Ground crew. Now in ground department, we have to learn this very hard way. It's like, you may be like, how the heck a company that is made up of Boeing, Lockheed Martin have a rocket that is like half the power and double the cost? Is because of this goddamn building, meaning horizontal manufacturing assembly, final assembly building. Now what they try to do is basically make the rocket horizontal as the moment they make it into stage, meaning now it's done, they make it up, and then they carry it in this orientation directly to the main assembly building, and then they actually pull up the rockets, attach the side boosters, attach second stage, all that. Now you're like, wait a minute, that sounds expensive. Yeah, it is. And that building, think of it that building has to sustain cranes, very expensive cranes, and like you have to lift whole stages on that. It's super expensive. So that has to be gone. Like that's why SpaceX is so efficient. Is like, ta-da! Like if you looked at any Russian launches, you will say like they are using normal train, and then they're like, done. That's the whole thing. No longer like that vertical. Now some military satellites require it, and again, in case Indian military is also like, no, we need something like that. No problem, no problem. It's like, because be mindful, second stage is much heavier than the payload. Second stage is huge, heavy. So instead of that, they're like, okay, a much smaller, much more trimmed down variant of that mobile tower is just like done. That can be done. Again, that will be done once it's successful, not in the day one. That will be once it's successful. Now ground 2 can also set up like as quickly as possible extraction of O2 and N2 on site. Now you're like, why? Well, reality is this is one of those things that you want to need boatload of, and if you are buying it from someone else, all you are doing is paying them for the electricity that they are using for running their air distillation unit, and their profit and their transportation. So you can cut these two sections out of the mix, transportation and their profit. And again, if they were not making profit, whatever company that you are buying from, if they're not making profit, why the heck they will sell you? So you get that point. Like you can make it cheaper, because again, air is available everywhere, and as long as you have power, you can literally get the O2 and N2 directly on site, and you can store it, and you can even shut down the plant. It's like, hey, I don't need it right now, or you can sell it to other people also, which SpaceX is actually planning to do in Boca Chica. So you get that point. Like this is one of those things that can be done on site. It's like actually efficient. Again, the capital cost goes up, but running cost goes down significantly. And then one of the long-term goal would be Sabatier reactors planned for CH4 production. Like, why the heck making CH4? Well, CH4 is much cheaper compared to RP1. It's still expensive. It's still there are only few natural gas wells there, majority of them in Russia, and again, Russia can increase the price, which they have done recently. So you get that point. Like natural gas prices can go up and down, and when you are buying tons of it, it does translate to the final cost. And again, CH4 is not something that will like tada. And even the CH4 that you are getting there is not very, very pure. You still may have to send through multiple stages of basically filtration to make it absolutely pure. Now, is it necessary? No. It will do is like give you some specific impulse, efficiency, some efficiency boost, and you're like, there will be some improvement, not too much, but again, from that CH4 development gives you control. You all you have to deal with is electricity bill. Now, India is going fast in renewable energy sector also right now. Solar specifically, we are going YOLO on solar, as in like 2,000 megawatt solar farms, and like there are other plants that are being worked on that are like 600 megawatt, 700 megawatt, and 20,000 megawatt. Yeah, like bonkers amount of solar. Now, here's the deal: that it will, like, literally it will create a scenario where will have too much daytime production. Now, if ISRO, again being a government agency, does have the luxury of working with other government agencies, like ISRO already does that. Like they deal with army, they deal with basically agriculture department, they can deal with that. So they can have a, like, sharing budget kind of scenario with basically energy department. Because if this is done properly, if we figured it out, if we made it into a, like, a proper unit, industrial unit, this is basically taking electricity, make it into chemical energy. So during daytime, rather than shutting down all the solar farms or overproducing, they can just make CH4, and CH4 is much more storable even for very long term. Like you can just energy overproduction has when you just keep storing it, because more and more people are adding renewables have like that intermittency. You never want to shut them down, but what the hell you gonna do that? CH4. Now, like, where the heck you will convert CH4 back into electricity? India already has a lot of natural gas plants which uses jet engine. Jet engine love methane. They love methane. You give them methane, it's like, I got this, fam. So we have how to convert, like, we are talking about like megawatts of power. It can be done. So that's why, like, that is advantage to the nation. On top of that, this is a core level technology development that we need to do if we want to build large scale space station. Like, wait a minute, what it has to do with space station? Think of this, like when ISS was first built, they did what any submarine does, is like just have energy, electrolysis, tada. Now, problem with that is A, it makes hydrogen. B, you need a boatload of water, like boatload of water. So what NASA does right now is like basically older variant of MOXIE. Basically they carbon dioxide, make it into carbon monoxide, spare oxygen. Now they do not directly use that. Like they take the carbon monoxide and react it with hydrogen. At certain situation you can do that and you can get CH4. Now you have taken care of the spare hydrogen, you have made methane, and all you have is spare oxygen. So not only you are getting oxygen back from carbon dioxide, that's the important part of it. So that's how they can extend the stay capacity of ISS much longer. Before that, like, they had to carry boatload of water. Now they carry very small loads of hydrogen. Again, they carry a lot of hydrogen, but hydrogen is light. So that's what, like, we have to develop this sort of thing. Otherwise, like, you simply cannot build habitats in very far out space. It's like it's gonna run out of oxygen and carbon dioxide poisoning. So CH4 is the very awesome way. And there are some plants in progress that can break CH4 and get like carbon as a, like, graphite powder or some carbon composite, and you'll have hydrogen independent. At that point you have complete cycle, meaning you do not have to worry about it. You just keep again, at some point even you will run out of carbon, but very long time. Like at that point it will be completely closed loop. We have not reached that yet, but it can be done. So that's why, like, the CH4 development is a very crucial thing, not only for the nation, also for space development. And then we have to understand this aspect, because this is a big project. It's going to consume boatload of metal, it's going to consume boatload of nitrogen, and again, from day one you're not going to have this air distillation. Again, these things have to be done. So a rail link may be developed, needed, that will allow, like, much easier transportation, much reliable. It's far more reliable. And landing and launching pads can be built from day one. Those are, like, dumb things that can be done from day one. So that's the ground string. Again, be mindful, there are many things that can be done on parallel. For example, the computation department is like, okay, we go to India's department that is dealing with IT sector. It's like, okay, there is a RISC-V variant of India's processor, that is a Shakti processor, completely made in India. And then we talk with that. It's like, okay, can you make a 250 nanometer variant of that? Now, like, why that high? Well, those things are far more resistant to cosmic ray bit flip. So that's why you really want a huge chunks in transistors. Basically, you never want like 5 nanometer. Again, if you send 5 nanometer CPUs in the space, it's like it's gonna get bit flip. That's why, like, the radiation hardened equipments are generally much fatter, like 200 nanometers or even 400 nanometers. Like 100 is like bare minimum. So you get that point. Like, again, that will also take time. But again, if you're starting it from day one, you can have it done at the 2-year mark. It's like everything is done parallelly. It's like launch pad, we got this. Supply of oxygen, nitrogen, and methane, done. Now methane maybe take longer, but you get that point. Like, at least oxygen, nitrogen, done. Tank, done. It's like the moment engine starts to ship off there, even Mark 1 engines that are like just testing and going boom, that will still teach you a lot, and you can refine everything parallelly. And at the end of like 3 or 4 years, you will have a fully finished rocket. That's how SpaceX is doing it so fast. Now, philosophy change is the main thing that I want to impart on ISRO. Right now, ISRO's philosophy is they have never moved past 1970. It's like somebody from 1970 taught them, like, that's how we build the rockets. Again, at that point in time, we did not have big, powerful engines. B, we did not knew enough. Right now, we have learned, and that was the light bulb moment of SpaceX. It's like Elon Musk looked at, like, actually looked at it. It's like, dude, none of the engines are new. All of the engines are like from the Cold War era, and nothing has changed. That was his light bulb moment. It's like, holy damn, everybody is stupid. And when he realized that, it's like, okay, I'm gonna make myself some rich money. So he did that, and that's the whole point. We have to talk to ISRO and, like, okay, what's your philosophy here? Philosophy: reduce the goddamn part count. Meaning, you cannot have, like, okay, there is X configuration, there is XL configuration, there is triple X configuration, there is Y configuration. No, one rocket, done, go home, sweet dreams. And machining time, this is the another aspect. Like, this sort of CNC hyper expensive machines, no. Like, again, for small parts, for some integrated details of the engine, some development you gonna need this, but some, not the whole tank should be built out of this. Like, that's why, like, I have provided a video down below, you can check out, like, ULA, like, they will show you the machine that this puppy is. It's like, you look at it and you're like, yep. That's why you like, literally, your rocket that can barely put 30 tons to low Earth orbit will cost same as SpaceX, that can put 100 tons. That's the whole reason. Like, just that tank machining, this is just for tank machining. They take this thick aluminum and it's like, poof, what? So that's one thing. Like, these things have to be in the core. No parts count. Like, reduce the parts count, reduce machining time, and supply chain. Now, this is one thing that Elon Musk, being a software development, really did help you out, because, like, software development team, they start out with everything spread out and then they try to collapse everything as quickly as possible. And he did that, and he realized, wow, everybody is stupid. So that's the one. Another thing is, like, try to do as many things in-house as possible, and things that will be basically non-salvageable. For example, fairings, it's not worth it to recover. Again, will not make it out of basically carbon fiber. Try to make it out of, let's say, steel if it works. If it does not work, aluminum. And again, it will be much smaller compared to the main rocket, so it will not be too expensive. And rather than, like, machining it, which is right now the convention, you can utilize some modern development in basically stir welding, and you can have, like, panels, and then you can have ridges inside that panels. And so basically, like, how your car is built, like, it has a smooth side and a bumpy side that provides the structure. Same can be done with system of basically fairings, so your fairing will not be too expensive. And no goddamn boosters, no boosters. Like, just a smooth rocket, just smooth rocket, go home, done. No smooth boosters, like one booster for, like, a little bit of push, two boosters for a little bit more push, four boosters. No, just either the rocket is powerful or it's not. No more boosters. Like, adding boosters is not as easy you may think, because again, the core has to be redesigned, rebuilt every time, and the software has to be re-upgraded, configured. Those adds point of failure and cost. Not, it's like clean rocket. And adaptability in design, this is one thing you have to understand. Many companies, once they build the rocket, they're like, settled down, it's like, we got this. But every company that is succeeding and adapting, they are like, what they are doing is like, we have developed it, how about we push it? Like, this is Falcon 9. Many of you may like, wait a minute, that engine does not look right. Yeah, that was block 1. It was like, at that point in time, 10-ton capacity. They learned it, like, they built it. It was still working. It was still winning actual NASA contract at that point in time. So, but they still did not stop, which every other company, like big companies, did. But they did not stop. They're like, what if we push it further? What if we made it octogrid? What if we did this and that? And by the time they are block 5, they are like, we got this, fam. So that's the philosophy of it. Like, once we get it done, like, that's the first point, like, get it done as quickly as possible. Once you start launching it, once you figure things out, once you nailed on everything, then you refine it. You do not be like, okay, it's done, go home, don't touch it. That should only be done once you achieve human rating. At that point in time, it does make sense, don't tamper with it. But everything else, go YOLO on it. So this was my very long video. Hopefully you have actually watched it till this point. At that point in time, I am eternally grateful for you. But like, again, if you liked it, learned from it, enjoyed it, I would urge you to press like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment, or 3 times, or leave a comment, because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.